In our last video, we talked about the subspace topology and saw that it could be quite a complicated topology to work with. Now let's find the relation between the subspace topology and the product topology. In particular, we're going to have a look at this theorem. Let's read the theorem and then explain it. If A is a subspace of X and B is a subspace of Y, then the product topology on A times B is the same as the topology A times B inherits as a subspace of X times Y. This theorem can be very confusing, so let's split it into different sections. First we have A is a subspace of X, so this sentence means that we have X, a topological space, let's call it with a topology tau X. A is a subset of X, and because it's saying subspace of X, it means that we have defined in A the topology tau A induced by the topology tau X. So we have the topology tau X and the subspace topology tau A. If you don't remember about the subspace topology, first watch the previous video. Then we have B a subspace of Y, so the same with Y and B. And then it says that the product topology on A times B is the same as the topology A times B inherits as a subspace of X times Y. So first we have the product topology on A times B. This topology is the one with bases, let's call them U times B, where U is in the topology of A, so in the subspace topology of A, and B in the topology of B, so again in the subspace topology. And then it says that this topology is the same as the topology A times B inherits as a subspace of X times Y. So first we have the topology of X times Y. This is going to be very similar to this, only that it's generated by the U times B with U an element in tau X and B an element in tau Y, and the topology A times B inherits as a subspace is going to be the subspace topology inherited from this one. So this topology, from what we've seen in our last video, is going to be A times B intersection W, where W is an element in the topology of the product space X times Y. We can, without loss of generalization, suppose that U is going to be one of these elements in the basis. So W is going to be U times B, and we can use that to prove the theorem. What the theorem is saying actually is that these two topologies are the same. They don't seem the same, but it actually makes sense. I know that this theorem can be very complicated to understand because there are a lot of topologies in here, so it's very useful for you to pause this video and try and write down all the definitions that are taking place. Now let's continue with the proof. Let's call tau A times B the product topology on A times B. Tau A times B is going to be the one generated by product of open sets in A and in B, and let's call A times B supra S the subspace topology in A times B. TS A times B is this one. To prove that these two topologies are the same, we will have to prove the double inclusion. But it's actually extremely simple to prove this, because if we take an element in the tau S A times B, this element would have to be, like we say here, A times B intersection W, where W is an element in the X times Y topology, in the product space topology. So we can, again, without loss of generalization, suppose that W is going to be of the form U times B for U in the topology of X and B in the topology of Y. We can do this because W is actually going to be an intersection or union of elements of this form. But for the calculations that we are going to do, this doesn't affect much and it actually just complicates everything unnecessarily. So A times B intersection U times B for U in tau x and B in tau y. This is an element in tau A times B as a subspace because we're taking the intersection of the space in which we want to work with a set in the space topology, in the product space topology. But now let's see how we can write this set. This is equal to A intersection U times B intersection B. And now A intersection U, because U was in tau x, A intersection U is going to be in the tau A topology. So it's going to be in the topology of A as a subspace of X, simply because it's A intersection an open element in the X topology. So this is an element in tau A. And the same for B intersection V. V is an open set in the Y topology. Then V intersection V is going to be an open set in the subspace topology of B. And so because this is an equality, then immediately we get from this an equality in there. So the proof was extremely simple. All we needed to do was note each definition and use a proper notation like the one I used here. The same will happen with most exercises in this chapter. Maybe they're not hard to solve, but the notation is everything.